Okay, we've got part two of exponent rules here. We went over before multiplying like bases. We also went over dividing like bases and power of a power. What we're going to do in this this part of the concept notes is we're going to take a look at some more interesting things that are namely an exponent of zero and negative exponents. So right now, you can remember from before that if you had this expression like, let me give you z raised to the fourth power, you could just take that and say, well, that's z times z times z times z. Or if you had something like, 3 to the fourth power, that would be just 3 times 3 times 3 times 3. So our question is now, what if, and by the way that would be 81 I think, 3 times 3 is 9, 9 times 9 is 81. What about this? What about this? What if you had, let's go 5 to the 0 power. So remember that our exponent tells us how many times we're supposed to multiply the base. 4z is being multiplied together here. The 3 is being multiplied 4 times over here on the right hand side. But a 0, if we use our definition we had before, wouldn't really help us. Or, how about this? How about 5 to the negative 2 power? How many times are you supposed to multiply 5 by itself? It's not 2. It's not a positive number, it's a negative number. So to help you to understand this concept a little bit better, I'm going to show you a little pattern. And the base for this pattern is always going to be 2. So I'm going to write a 2 here. I'll write another 2 there, 2 here, and a 2 there, and a 2 here. And I'm going to raise this, and I'll try to use a different color for this. And we'll go with maybe, let's see here, how about red for the exponent. So let's raise this to the third power. We'll go second power, first power, 0, and negative 1, and then we'll probably extend this a little bit as well. And I want you to see what's happening here. The 3, 2, 1, 0, negative 1. All we're doing is just subtracting 1. So from 3 to 2, that would be subtract 1. So that's our pattern on the exponent side. That's all we're doing. If we take a look at what these things are actually equal to, this is 2 times 2 times 2, which would be 8. 2 squared would just be 2 times 2, or 4. 2 to the first power is 2 times itself only once, which is just 2. If you look at this, though, on the right-hand side, let's take a look, and we're just going to look down the right-hand side. So what is happening from here to here and from here to here? Well, from 8 to 4 and from 4 to 2, it looks like we're dividing by 2, or perhaps a different way to think about this is multiplying by 1/2. 8 times 1/2 is 4. So if we take the previous number and we multiply it by 1/2, and that gets us the next number. And this pattern continues. 4 times 1/2 is indeed 2. Remember that we don't really know how to deal with these just quite yet with our definition of an exponent. So let's go ahead and let's just try to extend this pattern. We're going to see what happens here. So if we want to get this value right here, what we need to do is take the previous value and multiply by 1/2. If we do that, 2 times 1/2 is, well, that's just 1. So it looks like 2 to the 0 power is just 1, and that is going to be something that you're going to want to remember. So let's write that over here on the right-hand side. So with an exponent of 0, so any base with an exponent of 0 that is equal to 1. Believe it or not, it's not 0. 2 to the 0 power is not 0. We can see that here, that we're just multiplying by 1/2 every single time, or dividing by 2, whichever way you want to think about it. And 2 to the 0 power is definitely 1 if we use that pattern. Turns out that any base with an exponent of 0 is equal to 1. So even if you had something like, I don't know, x to the 0 power, any number to the 0 power, any base is just 1. you could do this even with some different bases. Let's say you had 1/2 a, b, c to the second power, all raised to the 0 power. So the 0 is applied to this whole base. That is just 1. Any base with an exponent of 0 is equal to 1. Let's go back to our pattern and let's continue this a little bit further. We're going to go ahead and take that 1 and we're going to do the same thing. We're subtracting 1 here on the left-hand side, on the exponent side. And we're just going to multiply that by 1/2. Same thing we did here. The pattern remains the same. Subtract 1, multiply by 1/2. And you can tell now that 1 times 1/2 is 1 over 2. And I'm going to help you see what's going on here and put a little 2 to the 1 down there. Okay, 2 is the same as 2 to the first power. It looks like the base stays the same, but we move this to the bottom or the denominator of the fraction and the exponent becomes positive. That is another rule that you're going to want to remember. So if you have a negative exponent, what you can do, and so we'll just kind of write an arrow here. So if you have a negative exponent, you can move the base and the exponent to the other side of the fraction. And you also have to change the sign of the exponent. So I'll give you a few examples here. If you take a look at this one, if you take a look at 3 to the negative 3 power. Well, really, that is over 1. So if we write our fraction bar, we're going to take the base and the exponent, move it down to the bottom, and then change the sign of the exponent. And so that negative will be a positive. And it's 1 over 3 to the third. With a number, you can actually go ahead and do that arithmetic or that math down here. So 3 to the third is just 3 times 3 times 3, which should be 27. I'll give you another one here with a variable in there. Let's say you had 1 over, we'll go t to the negative 7 power. What you can do is you can just move that to the other side of the fraction, change the sign of the exponent, and then it's over 1. So really we don't need this division by 1. You don't want to write division by 1 as a final answer. We're just going to write t to the 7th power. I hope you're okay with my funny looking t there. That's just how I write them, or else my t's look like plus signs. So 1 over t to the negative 7 is really just t to the 7th power, and those are equal.